Hello guys, in this video I'm going to show you how to solve reconstructing a sequence. So given a sequence, original sequence, and an array of sequences, write method to find if original sequence can be uniquely reconstructed from the array of sequences. Unique reconstruction means that we need to find if original sequence is the only sequence such that all sequences in the array are subsequences of it. Okay, so with this given input 1, 2, 3, 4 sequences 1, 2, 2, 3, 3, 4, the output is true because the sequences can uniquely reconstruct 1, 2, 3, 4, right? In another word, if the given sequences uniquely define the order of numbers in original sequence. Alright, so this problem seems to me like a graph problem, right? Whereas in which each number here can be a node, right? And we may want to represent it in graph. Then apply topological sort on those nodes, right? So while doing topological sort, we can have different orders, different orderings based on these sequences, right? And the thing that we want to check here is that if these sequences can produce the only one sequence that is the same as the original sequence, then want to return true for these functions. Otherwise, it's gonna return false. Okay, so let's start. With topological sort, we need two graph, right? First is graph. Now we need one graph, which is a map, right? And incomings. This one will also a map. This one will store key and value in key and value in which key will be the node, the number itself, and value will be the dependencies or incomings, the number of incomings or vertex. I forgot it, but anyway. Okay, so firstly to initialize our graph, right? Need graph and incomings. We can use the original sequence to initialize the graph, right? Okay, so we'll let vertex of original sequence, then each number will be one vertex, then I will add it into a graph, right? I will set the vertex. The key is a vertex and the value will be an empty array, which later will be filled up um, with destination vertex. Here is source vertex because we are represent our graph in adjacency list. Right. So for incoming, it will be set it with 0 initially. Right. So initially, for each vertex, there will be 0 dependencies. Okay, next step is to okay, wanna wanna doing wanna be doing wanna do topological sort based on these sequences, right? So build graph and incoming from sequences list, sequence of sequences list, and each of these I'm gonna look through this one, right? Like it is not necessarily 2 items here, but it can be it, it can have multiple vertex here, so we need to look, right? Another look inside here. Wanna wanna check each pair of vertex, right? Because 2 vertices will form a uh, 2 vertices can form a dependencies, right? One depends on the other. So here I will use a traditional for loop here. Want to start from 1, right? Because we want to compare the not compare, but wanna pair up the current with the previous. Right? I less on the second of name I plus plus. Okay, so the current vertex, let's say the destinations to be more exact here. Destination will be sequences at index I, and the source vertex will be at index -1. Right? So from these 2 vertices, we can feed to graph and income is here. Okay, graph. I can get the source vertex. It return a session list so that I can push the destination in, and also I want to update the destinations vertex here, so I will increase its dependencies by 1, so I will get the current value and +1 here. Okay, after these 2 loops we have a graph, and not graph here but incoming. Okay, Next step is to want to start uh, do want to start do topological sort, right? So the output of topological sort will be orderings, right? I will store the result in the ordering. Ordering will be an array. Right? Um, Ordering is just a sequence of vertices that is in certain order, right? So for topological sort, we want a queue, right? I'm gonna call it sources here. Queue in JavaScript can be an array where enqueue will be pushed and dequeue will be shipped. Okay. Wanna initialize the sources here. So the sources will be storing the next vertex that will be put that can be put in the ordering here. So the one thing in common of vertex, but the vertices that can be put in the sources here is that they all have the dependency of 0. Right, so I will check the incomings here. So let incoming is a map. So the key could be the vertex and the value will be num of dependency of here we can use utility functions entries so that we can have vertex and num of dependency here. Next is to check if number of dependency is 0, then this vertex is a candidate to be put in the sources. Push in the vertex. Here we can start doing topological sort here, but here we can one shortcut we can do a check here, which is if the sources length is greater than 1, which is there more than one way to there more than one way to there more than one way to put the first vertex in in the ordering here. So which means it will result in more than one ordering, right? So which means we cannot produce a unique sequence out of these sequences, so we can just return false right away. Return false. Okay, if it if it comes here, it means that there's one vertex in the sources, so that we can start processing here. So as long as we have something in the sources, I can start pulling it out here. Actually, this can be put inside here, I guess. So if the source is not length is greater than 1, which means there are more than one way to for the ordering here, right? We don't return false, otherwise there's one sources here. So I can take it out. Vertex. Next vertex will be sources. No, shift. Okay. This one I will put in the ordering. It's the next valid one to put in the ordering. So ordering dot push vertex. Next vertex. Actually, as we're building up the ordering, right? The perfect case would be here at the final. The ordering will be the same as original sequence. We could be a perfect case that in which we will return truths, right? So as we're building the ordering, uh, we can keep checking, right? If the current state of if the last value of the orderings is equal to the corresponding in the original sequence, right? If it is not, we can return early. So here at the push in the ordering here, I can check, right? I want to check the last one in the ordering here, which is ordering dot length -1 is equal to the item with the same index, but in the original sequence. If it's different, it means we cannot build the original sequence, right? So we just return false here. I can abstract it into last index. So otherwise, if it comes here, it means it's still good until now. I can just I need to update our dependencies, right? Our incoming map here, because this vertex has been taken away, right? So I will update all the vertex, all the destination vertices that coming from next vertex. I will decrement number its dependency by 1, which means I'm gonna check all the destination vertex from the next vertex here. Okay. So I will update the incoming of this one equal to its current value minus 1, and if it after these operations, if it reaches 0, it incoming, if the dependency of these destinations is 0, then it's gonna be the next one to put in the sources, the next candidates. Destinations here, and at the end, after there's nothing in the sources, I can return choose, but not enough, I think, because the number of, if we exit here, it still doesn't mean the ordering and the original sequence is the same. We need to check the size of these two also. So the ordering dot length equal to is that equal to original sequence dot length. If it is, it means it is the same as original sequence, and we return true, otherwise returns false. Okay, I'm gonna run the test here. This will be 16 and 5. Hopefully it will work. Okay, awesome. It is awesome. So just need to double check. Okay, perfect. So that is it for this video. Reconstructing a sequence using topological sort. Thanks for watching. See you in the next video.